what I'm going to talk about today is basically this tree search algorithm, where we build from a state space this search tree. And the question how to build the search tree is given as a strategy for solving this search problem. And the algorithm is written here in pseudocode. We basically have a function which takes a problem and a list as input, and it returns a solution or failure. Most important notion is this list, this fringe, which contains all the nodes that still need to be explored, so in our search tree. And what we then do is we have an instantiation phase, so we insert the initial state node of the problem to the fringe. And then we look at all the possible successors of this first element in the fringe, which is the only element at the time. If there is no successor for this node, we return failure. If there is a successor, which is a solution, we return this as a solution, and otherwise we have to extend our search tree. And now the question is, how do we extend this search tree? Extending the search tree means adding new nodes to the fringe, and how we do that determines how we search in our search space. And the sort of most simple way of doing this is called the breadth-first search, and that is basically implementing the fringe as a FIFO queue. Who knows what FIFO stands for? First in, first out. Yes. So basically, it's the notion of a queue. In this case, we start from a problem where we have the root node, which is A. We put it in, and that is our first iteration. Then we take it out and we look at the possible successors of A. And these are B and C. And what we do is we add them to our fringe. Yeah. So now the question is, what is the next node to expand? And that is the one that is first in the list. Yeah. And I look at the successors of B, and I add them to the list. Suppose that none of them is a solution. Yeah. And then I take out the next one in the fringe, which is a C. See it here. And you add the successors of F and G. And so on and so on and so on. And basically, by using this data structure of a FIFO, of a queue, you get the behavior that you start with the top, and then you explore the first level, and after that you explore the next first level. Basically, you explore breadth first, the level of the search tree. Yeah. So suppose now we have this simplified Schnapsen version, which is just about we have a hand of cards, and we want to reach a certain number of points, maybe more than 20, and we have to choose which card to play first in order to get to more than 20 points. And what you basically do is you look at the situation where you played the first card, you look at the situation where you played the second card, the third card, the fourth card, and the fifth card. And basically you put all those 5 states in your fringe, and then you evaluate the next one, and you look at all the 4 combinations that you could have. So this is a jack, I think, yeah, jack, queen, and so you could now play the jack, the queen, the ace, and the king. That gives you 4 more states you can end up with. And in this case, you can stop there because you have found a solution. I'm missing one there. So you first would have to explore the one where you have played the jack, then you have to explore the one where you played the queen, and when you have the one where you played the ace, you found a solution. So we now found a solution, a path from the initial state via this decision. I think I even get arrows here. So my path to getting to playing more than 20 points as quickly as possible is found by exploring. I should have taken these two as well. And then I find the solution. So basically, if I want to play at least 22 more than 20 points with as little cards as possible, I can just play first this ace and then the second ace, obviously, and then I get to 22 points. It's trivial from a human perspective, of course, because you would always use the highest cards to play out. But for a computer without any additional knowledge, this is not so trivial. It's a sort of a systematic, we found the solution by systematic search.
Question.
Yes?
Can we play it, or will that take too long? Can we play out this scenario on like there?
Sure. So I call the first one A. Yeah, so I don't want to draw them. So I have my top one. I look at which of those, from which state can I get by playing a card out of this hand. And then I get 4 ones. This is where the B would be this one, C is this one, D is this one, E is this one, and F is this one. I've forgotten one, of course. Yeah? So this one has already gone because I did the exploration. Otherwise, I wouldn't have found the BC, the top 5. So now I have this situation, because now I want to explore the B. And the B was these 4 cards. Yeah? So I now have 4 possibilities. I can play the jack. I can play the jack. I can play, what is it, the queen. I can play the ace, and I can play the king. Yeah? But that gets me to 3 new states, namely, what would it be? Queen, ace, and king. This one would be jack, ace, and king. This one would be jack, queen, and king. And this one would be jack, queen, and ace. Yes? So then I give the names. So this would be G, H, I, and J. The nodes now. And I would add them to the fridge. G, H, I, J. Yeah? So now, looking at this state, I know that I'm done. It's a solution, because I've played twice an ace. So this has a value 22 and is a solution. So I can stop expanding. I don't need to expand the C anymore, because I found a solution. Suppose now that I would want to find 25 points, so this wasn't a solution, I would have to go on. And that basically would mean I need to take out C. C was this one. Yeah? And then I have the situation that I have, again, the 4 cards. And I would have to do the expansion of all 4. And then I would first play what is it then in this hand? I have an ace, I can play an ace, a queen, an ace, and the king, in order to get me to 4 new situations, and I would have to add them at the end of the queue. Yeah? So it's very simple. It's just the only thing you need to remember is that this data structure always adds the things at the end, and the new things to explore takes from the beginning. And that allows you to explore all the nodes systematically, level by level by level, until you found a solution. And here I'm quite lucky that I found a solution so early that this was a solution just for the sake of making it fit on the board. So now we had the question yesterday, just a quick recap. If I want to explore sort of the 3rd level of the tree to find a solution, and I didn't find a solution earlier as I did here, how many states do I need to explore? How many things do I need to have in my list in the end, in my queue? So I hear 120, and that is 5 factors. So this was now the case where we don't take back cards. If you go to the first part of the game, you get your cards back, and then basically instead of having 4 options here, instead of having 4 options, I would have 5 again. So how big would my search space be if I would always refill my cards? 302. Say it again.
3,000.
Okay, and that is 5 to the power of 5. This is now if I explore until the end all 5 levels. So if you have to explore to the 3rd level, it would be this number. Yeah? So it is always the branching factor to the power of the depth that you're looking for. In the case that your branching factor remains the same. Here the branching factor, in this case, gets smaller. So the calculation of the number of nodes that you have to explore gets is smaller. Yeah. So why I was asking this obviously is the question, how efficient and how good is an algorithm? That depends on how many of the nodes do you have to explore before you find a solution, and how expensive is that. In this simple case, when you only have 5 cards and very few actions, it doesn't really matter that much. But if you have 10 cards already, we're really getting already into some kind of computational problem. So in order to understand that, we want to look at the complexity of the algorithms of search. So our strategy can be measured in different ways. The first one is completeness. The question is, do I always find a solution if there is one? Yeah, so that's a question of completeness of an algorithm in the search problem. The second one is optimality. Does it always find the best, the least cost solution? So here we haven't defined the notion of cost, that will come later, but for example, you could say the number of cards that are played are my cost, and then you want to find the one that is most up in the tree. The question is, does breadth first search always find the best one according to the cost of playing the fewest cards? The third thing you want to measure is the time complexity. How long does it take? How many steps do you want? And you don't want to measure that in seconds, but you want to measure it depending on the number of cards or the number of the properties of the game. So in this case, we can measure the complexity of the time that it takes to find a solution by the number of the branching factor. So that's the branching factor B to the power of the depth of finding a solution. So that is the time complexity measure for depth first search. And I use this O notation, which is this sort of simplification of the way where you take away all the sort of small prints and the plus ones and the times 5. This is the most important order of magnitude kind of information you have about the algorithm. So that's in terms of time complexity. And now the question is, how much space, how much memory do you use for your algorithm? And in breadth first search, you have a lot of things that you have to write in the fringe. So here we have taken off 3 of the, I don't know how many. But if we go now one level lower, basically it turns out that we have to put in memory almost all of those nodes that we have to visit. You can take off very few. as compared to the ones that you have to store. So this is the time complexity. And if you take the space complexity, it's comparable. And I can tell you that for real search problems, this is really deadly. Time is something where you might say, okay, I can wait, and we have very, very efficient machines. But if you look at this table, it's a very simple memory. It has been an experiment for how many nodes do you need to store for a certain tree. I think, I don't remember exactly what it was. It was, I think, breadth of 10. And then think of how deep you go in terms of time and in memory. And if you look at sort of the number of nodes that you get in order to calculate, then this was, I think, 10 years ago. So I think we would now calculate this depth 10 with 10 cards with 10 to the power of 10 or 11 nodes. We would be able to do that in a reasonable time. But we would not do that on our laptops with terabytes of data. Even if we would store this very efficiently, there is no chance that we would look at a tree, a search tree of 10, so branching factor of 10, systematically to the end with breadth first search. So imagine now you implement the same game, a simple, stupid game that I had with the 5 cards where you want to play and you want to check out whether you can find what the values are. This is already becoming computationally impossible because of this part particularly, the space problem. So therefore, or probably also because it's the logical way of doing things, people have looked into other ways of dealing with the search. And there is the depth first search. And if the one is the breadth first search, you can already imagine what it does. It goes depth first, searching for a solution until it reaches the end of the search space. And basically, you do that by a very simple trick, and that is you use a different data structure for your fringe. And that is a queue, or a stack, a LIFO queue, and that is now last in, first out queue, which is also known as a stack, as a data structure. So let's see how that works. We have our data structure is not a queue now, but it is a stack. Yeah? So we start with A. Put it in our stack, and we take it out and expand it. What do we get? We get B and C, so in order to keep with the order of how you put in that is might be confusing, but you can choose in principle how to add them to the fringe. And then the next step is you take the top one. You always take out the top one from this stack. This is B in this case. So now we look at expanding B, and we add E and D. Yeah? You see how this works? We again take out the top of the list, and we expand the top. And we add I and H. So we take the top again. The top has no things to explore anymore. Suppose we haven't found a solution yet. Then we take the next one in the list. And that is then the I. The I also does not have anything to expand. So we take it out. Now the top of the list is the E, this node. And we can add new stuff to the stack. So if we expand E, we get, so this one we've done. If we expand E, we get J and K. So we add J and K. And again, we look at J, is it a solution or it's not a solution, and so forth. Yeah? You get the principle? And that basically gives us a way of exploring the tree from the root to the leaves in one go down here. Then it does something that's called backtracking. So if this is not a solution, I have to go to the next one and look right in this case. If this is not a solution, I have to go back, and then the one that is again the best one according to the depth first search. And I do the same. So it's now, once I've explored all the J and the K, the next one in my list. So I see that E cannot be explored anymore, and then the next one in my list is the C, and I do exactly the same. Yeah. So basically, now if we do this with our Schnapsen example, the difference would be here that that at this point we would start exploring this node and not looking at all those, but we would only looking at this first one and would go on until we find a solution that we find in this case, namely the one where I first played the, what is it? Here I play the jack, so that gives us 13 points. Here I play the queen, that gives us 15 points, and then I play the ace until I'm in this state. And this is a solution because I've now played 26 points. Yeah? So I find a different solution with a different search strategy. And in terms of cost, I needed now not 2 cards to play out, but I needed 5 cards or 4 cards to play out to get to my 20 points. Yeah? So I haven't explored the tree in its full breadth, but I only explored one way down. Yeah?
Doesn't that give you a solution that might not be the least cost?
Thank you for saying. This is it wasn't a cue, it wasn't discussed beforehand. Indeed, this algorithm is not optimal. So you do not find the shortest path according to the depth of the tree. Yeah, so how many happening here? So that is the answer to the first question. Is it complete? Oh no, sorry, the second one. Does it always find the least cost solution? The answer is no. The first one is also interesting. Does it always find a solution if there exists one? Yes. I hear a very clear yes. So this is my initial state. This is the state A. I do depth first search. So I put the J in my stack, should start down here. And then I start at the A. And now I have 2 ways to go. I can go to the J, and I can go down to the S. So I put the S and the J in my stack. And I take out the J because I have to expand the J's, and that gets me an A. And I have to expand now the A, and we know that this was the S and the J. So I take out the J. And I think you see what's happening. I'm now building a tree which is J, A, J, A. And if I implement my depth first algorithm this way, where I don't check for duplication, then I might get into an infinite loop. Yeah? So basically, depth first search is not complete. Because if you implement it without extra knowledge, it doesn't always find a solution. Because this algorithm, if I implemented it this way, and the trick is, of course, that I put those 2 in a stupid order. I put S again in, and I should not have this one is the, yeah, I think, yeah. So I should not have put J again in, because I have already explored it. So if you do the duplication check, then you can avoid this. But you need to add extra knowledge. So the pure depth first search is not complete. It's not optimal. What about time complexity? So how many nodes do you have to explore in the worst case? All of them. And how many are they? Okay. So the time complexity is again in the order of the branching factor to the power of the depth where you find the solution. So if you do the breadth first search, you have one advantage, because what you can always find is the restriction that you only have to go to the depth of the first solution. Yeah. Here you might really have to explore the whole depth of the entire tree. Okay, so that is time complexity. What about space complexity? Are you the same? Does it? No, it doesn't. It only remembers the ones. You always have only to remember the ones that you need to explore next. Yeah? Yeah, you need to explore one, I think it's, what's the precise number? Oh, sorry? Yeah, it's more than just D. It's not linear. It's I think it's B times D. Yeah. So you need to do the depth, and then for the branch you need to the level that you have explored. You need to keep this. So it's bigger than the linear, but it's still completely different ball game between this and this. Yes, you have a question?
Yeah, if the algorithm is not complete, how can we have a time complexity? Shouldn't that just be, because you said you could get stuck in infinite loop, wouldn't the worst case time complexity then be that infinite loop?
D could be infinite.
Okay.
Good question. So here's the summary of the algorithms. So breadth first also could be, actually I cheated a little bit. Breadth first can also be incomplete. I think we didn't even talk about it. So breadth first could have a problem if you have infinitely many choices to make, and then it's obviously impossible to find the right solution. So if we consider a game that you pick at every move, you pick a number out of the rational numbers or the natural numbers, then I cannot even draw your search tree because I have infinitely many options to choose from. The natural numbers is obviously infinite. So I cannot explore the search space when I have an infinite branching factor. But as soon as I have a finite branching factor, so finite number of options, then my algorithm is complete. Depth first is not complete, and then we have the time, which is more or less the same. So here the D stands for the depth, where the solution can be found, the first solution can be found, and this is, I think, the maximum depth. The space complexity is really the big difference, because if you do depth first, you only need to keep one branch more or less with a little bit of overhead in memory. So that's a big difference. And on Friday, I will show you one of my favorite algorithms that sort of solves the magic of combining both the completeness of breadth first search and the space complexity of depth first search. Yeah?
So we started on the slide by tree search.
Yeah.
And the definition of a tree is acyclic graph. So how can we end up with this situation where we have a cycle?
I built a tree out of a state space. So this is my state space, and the tree I built is this, and this is an acyclic graph. So this is the search tree, and this is a search the state space. That's the difference I tried to explain yesterday at the end of the lecture. Okay, so. The question is now, of course, that in a way there was a very arbitrary choice made of choosing the cards, exploring them in the order that they were printed on the board. But why didn't I explore the A's first? And then I would, any algorithm, depth first or breadth first, would give me immediately the solution if I would always choose the card with the highest value. Yeah? So uninformed search just takes the cards in some order, and I use the order here in some kind of arbitrary way to cheat you into the algorithm working, saying here so that it fitted the same description. But in principle, there's nothing telling me that I couldn't use a different order in exploring depth first or breadth first. And this is the next step that we say we do informed search. Namely, we use a heuristics that tells us use this node first for exploration. Yeah? So informed search uses heuristics. What is a heuristic? And basically, it's the same. Either you do FIFO or you use a LIFO. Doesn't really matter. The question is, can we now decide on a better choice in my FIFO? Can I order basically my fringe? And I can do that by assigning a heuristic value to each of the nodes in the fringe. So this is called best first search. I just reorder my fringe, not in the order when did they come in, but in the order of according to some heuristics. So I have some evaluation function, and that could, for example, be in Schnapsen that I say, I take the value of the cards that I have in and I would play next as my heuristic value, and then I would just start with all the states here in the beginning which have aces, 2 aces to play out with. So basically this evaluation function or heuristics measures the distance to the goal. And then I order the fringe in decreasing order of desirability. And then there are some algorithms. The most simple one is hill climbing, but the sort of general idea is you always take the one that you believe is the best one and explore it first. So not in some kind of alphabetical order, but now by some order of hope that you think this is closer to my goal. So a heuristic function is a rule of thumb. It's a simplification. It's an educated guess. It's something that we humans come up with to feed our search algorithm in the domain. And they are very, very useful if we don't really understand the domain in which we're looking. So basically we have this h of n notation where we say h is the estimated cost of the cheapest path from a node n to the goal node. And when the goal is the node n itself is a goal node, then this heuristic function should have the value 0. The reason for needing this is that very often we don't have the complete knowledge, and it's, as we've seen already with these simple examples, it's too expensive to calculate. So we use some educated guessing, some human expertise to tell us in which order to explore the nodes in my fringe. And they can be completely wrong and not work. And I will show some examples. So you all know this sort of tiling game where you get a situation like this one, and you want to bring these tiles in a position where the one is on the top left, and then it's ordered. So that would be 1, 2, 3, 4, 5, 6, 7, 8, and the empty one in the middle. So top left, and then clockwise the numbers. And then we have different ways of estimating how good this is that might guide us to our actions in the search. So the number of incorrectly placed tiles is one heuristic that we can use. So how many are there? So 2 is incorrect, 8 is incorrect, 3 is correct, 4 is correct, 5 is correct, 6 is incorrect, 7. I might have done a mistake. So I don't know how to get to the 6 here. 1, 2, 3. The 8 is correct? No. I'm not sure I understand why it is the 5 here. Huh?
The empty tile, so 1, 2, 8, 6, and 7 are all incorrect.
Oh, it's the incorrect tiles. Yeah, sorry, I was counting the correct tiles. Yeah, so it's the incorrect tiles. Apologies. Yeah. So out of the 9, 3 are correct. Out of the 8, 3 are correct. There is a different heuristics, and that could be the sum of the distance of the tiles from the goal position in a Manhattan way. So how many moves do I need to make to get the 1, for example, to its right position? So I need to move the 1 up is 1. I need to move the 2 to the right is 1 more. 3, 4, and 5 are correct. The 7 moves here is another one. And the 6 moves down. And I think this the 8 also has to move. So we get to the 6 moves that we need to make in order to get there. And this is heuristics that's not depending on the rules of the game, because you can move here and you count the moves where, even if there are tiles. So it's independent of the game itself and how you would play. I have one more, and that is the sort of double the number of direct switches, and that will give you a value 0. Yeah?
First example, I count 6 incorrect tiles that are placed. Why do you say it's 5?
The empty should be in the middle. Even though it's empty, it still should be in the middle. So why doesn't that count as an extra one?
The question is whether the empty one is a tile or is not a tile. So you could count the 8-1 and then, but I think it's about the general idea. It might be the wrong number. It might not be 6. So don't judge me on that. Yeah. As long as you understand the general idea that depending on how you define these heuristics, you get completely different values, and of course you get completely different ordering of your thing. So then we know something about these functions, or we want to know something about these heuristic functions. We can, for example, order them by their quality and how informed they are. So the value that you should assign to a node should be between 0 and the perfect one. Suppose you know exactly how to come to your solution, then you can order them by some heuristic value function, h star usually, and then we have an ordering of just the values, how close are you there. And based on this notion of perfectness, on informedness, we can choose to find the right heuristic for our problem. And it's very often the case that the very simple, trivial heuristics are easy to calculate, but not very helpful. And the ones which are very, very close to the real solution are the ones where you need to do lots of calculation. So we always have to find a balance of, give me the one that is cheap to calculate, but still very close to the real solution. Let me check. Yeah, so I'm going to stop after this slide, then we'll have a break. Suppose we have this map of Romania again, where you want to travel from Arad to Bucharest, because the flight is going tomorrow. Then we know the distances, these small numbers that you would have to travel between the individual cities in the state space. And then we can base our algorithm searching on those and calculate exactly how long does it take us, how many kilometers or hours, and that would just be adding these numbers. But in order to understand which node to explore first, we can also use some more information. For example, what's called the B-line distance. And that is the B-line distance between my goal state of Bucharest and Arad. So if I would fly as a bee, that would be the distance between the two places. So Arad is 366. Bucharest itself is obviously in Bucharest, so it's 0. And then these are different values than the one that you would travel, but the B line is always the shortest. So that's very handy because it really gives you a good estimation of where to go first. And then based on knowing this distance, you need to know this actually. You need to look it up in a map. It's not, you cannot get this from this map here. You need to know this from some atlas or from the internet or whatever to inform your search. But once you know it, we can always use these heuristics to go first to the cheapest one, to the closest one, which has the closest B-line distance to Bucharest. And as we always greedily choose the one that is the closest to Bucharest, in our expansion, in the expansion phase, this is called the greedy algorithm. We always take the best and expand the best first. this is actually not the best strategy. And again, I'm talking about this on Thursday. I think I said Friday before, but I mean Thursday when I say Friday. So in the lecture on Thursday, we're going to look into the A-star algorithm, which is sort of the star algorithms of AI in the early years. How to do this really the best possible way to find not just greedy best search where you go to the closest place to Bucharest first and explore this one, but always really find the shortest path between a city and your goal in this application. So I'm going to show this search in a minute after we have a short break. Can we start again at 12 if that would be okay with you? Then I try to finish really in time. Thanks.